This problem asks to find the change in different values of a 1,000 kilogram granite block when it's heated from 25 degrees Celsius to 1,000 degrees Celsius. Since it's a solid and no phase changes are expected, the SL model is the best choice. So we'll want to go to Test Calcs, System States, SL model, and then either hit Test App or Test Calcs. And first thing you're gonna want to do is switch it to granite, which would be under solids right there, and then start entering your values. So actually, since we're gonna need to evaluate the Exergy, which is that phi right there, we want to fill out state 0, which is the dead state, or basically the equilibrium state. So P0 would be 100 kPa, and T0 would be 25 degrees Celsius. 25 degrees Celsius. All right, and then we hit calculate, and since it's state 0, the phi is going to be 0. And then state 1, P1 is the same, 100 kPa, or P0, and T1 equals T0, or 25 degrees Celsius, and M1 we're given is 1,000 kilograms. Right, hit calculate. Next, state 2. We're given that it is heated up to 1,000 degrees Celsius, and we're going to assume that mass and pressure are staying the same. So heated to 1,000 degrees Celsius, pressure stays the same, equals P1 or P0, and M2 is the same, so equals M1. And then hit calculate, and we get the rest of our properties for state 2. It's good to use equals P1 equals M1, or like in state 1 equals T0 equals P0, because when you want to change a value for the initial value, such as maybe it was 35 instead of 25 degrees Celsius initially, or 150 kPa instead of 100, you're able to just change it once instead of having to go through each state, and that leaves a lot of room for error. So this way is definitely the preferred way. Alright, so now that we have all of our values, we're able to go to the I/O panel to calculate the differences. So the first one asks the difference in stored energy, which would be E. But we want total stored energy, and in the state panel it gives us specific stored energy, which is the little e. We're looking for the delta big E, so we're going to have to multiply it by mass to get kilojoules instead of kilojoules per kilogram. So in the I/O panel, I'm going to type DE. You can use anything, any variable. I just chose DE because I think it's the easiest. And then, like I said, we need to multiply it by mass to get it into kilojoules. And then it's going to be E2 minus E1. Then you're going to enter or calculate, and down in the output area, you'll get your answer. And we get that the change in stored energy is 770,250 kilojoules. All right, and then the next question is asking for the change in internal energy, which is U. And again, it gives us little u in the state panel, right up here in kilojoules per kilogram. But again, we want it in kilojoules. So I'm going to arbitrarily choose du equals, again, times mass, and then U2 minus U1. Enter or calculate, and we get 770,250 kilojoules again. This is the same as DE because there was no change in kinetic or potential energy in the problem. So the next problem asks for the change in entropy, which is S. it gives us S in kilojoules per kilograms Kelvin. We want it in kilojoules per Kelvin, so we're going to multiply by mass. ds equals mass 1 times S2 minus S1. Calculate, and we get 1146.8 kilojoules per Kelvin. And now the last problem is asking for the change in stored exergy, which is kind of like the recoverable energy after this process happens. So it's going to be lower than the stored energy. All right, and that is given in the state panel as Phi2, which is in kilojoules per kilogram. Again, so to get it into kilojoules, we're going to do d Phi gets M1 times Phi2 minus Phi1, and then calculate, and we get d Phi equals 428,329.9 kilojoules.